Lesson 1-4. What we're going to talk about today are identifying key characteristics of polynomial functions. So let me start with this word polynomial. If you want to come to your notes, circle up the word polynomial. What this means is a function with multiple terms. A function with multiple terms. And you might be saying, well, what is multiple? I know that word, but what does terms mean? Well, I'll give you an example. An example would be like this. Y equals 3x squared plus 7. That's two terms. This would be polynomial. Two terms, okay? Or another one. Y equals 5x to the 7th power plus 2x to the 5th power minus 3. This is polynomial because it has how many terms? 3 terms. So that's what we're going to look at today, are polynomial functions, and we're going to identify characteristics from them. All right, on the next slide, you have just kind of a general rules for polynomials. It'll be a whole lot easier to explain looking at them in a moment, but for later when you look, these are your rules. So here's the big keys. Is whichever one has the highest power, is called the leading term. That's what this first thing is saying. So in this case, if n is the greatest power, if n is the greatest power, then this is true. Then a n xn is the leading term. It's called the leading term, whichever one has the greatest power. The n itself is called the degree. That's a key vocabulary term. That's probably the biggest vocabulary term of the day. The degree is the greatest power. So if n is the greatest power, then wherever n came from is the leading term, and we call that the degree. These things are also true. You could read over those later. The last one to hit is this. For polynomials, the domain is the set of real numbers. And there's the question why. Do this. Look over on my board, and I want you to look at the domain rules. There were 3 domain rules we talked about in the first math lesson. Do you remember what they were? Rule number 1, what's it say? Cannot divide by 0. Rule number 2, what does it say? Can't take an even root of a negative number. And finally, the last one. That's it. You cannot take a logarithm of a non-positive number. Polynomials are going to be all reals. If you're wondering why, it's because of this. A polynomial is not allowed to divide by a power of x. Or let me just say, it's not allowed to divide by the x variable. It is not allowed to have a root of x, nor is it allowed to have a log of x. Okay, so why is it all reals? Well, what makes a function not all reals is dividing by x, having an even root of x, or having a log of x. Since we don't have any of those 3 in the problem, then it's going to be all reals. It will be all reals because we do not have any of those 3 situations going on. Okay, so I'll give you a second to write that in. We will be all reals for that reason. There we go. A polynomial is not allowed to divide by the variable x. It's not allowed to have a root of x, nor is it allowed to have a log of x. And that's why it's all reals, because that's what makes something in the domain not all reals. Okay, here's just an example for you to look at for later on. Notice this says degree is 5. There's all these different powers. There's a power 5, 4, 3, and 2 that I see. Why is the degree 5? It's the highest power. The highest power is the degree. You need to know that, because that's where a lot of test questions are going to come from. They're going to tell you the degree. What does degree mean? Highest power. Okay, because the 5 is the highest power, this term right here is called the leading term. 3 would be the leading coefficient. If you ever hear the word coefficient, that means the number in front of x's or the constant all by itself. The numbers that are not powers, those are called coefficients. All right, so this is kind of giving you your rules that I have for the domain. The exponents cannot contain fractions. A fraction exponent is what creates a root. So here, fraction exponents, I'm going to write that in just so you know. A fraction exponent creates a root. And I just told you you're not allowed to have roots. That's because we're not allowed to have fraction powers. And the exponents also cannot be negative. A negative is what a dividing by x is. Negative exponents create division of x's. Division of x values. So that's why polynomials cannot have negative exponents, nor can they have fraction exponents, because that's what would create a root, that's what would create a division, and then we'd call it something different other than polynomial. We'll learn about this one next. They'll call that rational. That comes up on lesson 1-8. We're going to learn about rational functions. That's when you have a negative exponent. A fraction exponent comes out after that. That's when you have roots, square roots, third roots, fourth roots, stuff like that. We'll hit those later on, okay? So there's your rules. You can look back on that at your leisure. That's just an example, but I think a lot of this will make more sense just by looking and identifying when we look at a function if it follows the rules or not. So let's look at this first one, example 1a. Determine whether each of the following is polynomial. Explain your answer. What do you think when you look at this? Is it polynomial? Why not?
The degree of the third.
The degree, the power of 2/3. Now, technically, that wouldn't be the degree. The degree would be only the highest power, and 5 is greater. So technically, that's the degree. The degree here is 5. The degree would be 5, but great. I love how you're trying the vocabulary, but degree is reserved for the highest power. But you would say the power of 2/3. It's not polynomial. I'm gonna go ahead and write this in. Not polynomial, since the power of x is 2/3. You cannot have a fraction power. I'll put that in parentheses. You cannot have a fractional power of x. That is a rule. Now, by the way, you can have a fractional power or a negative power if it's a number, but just not on the x's. That's the rule. It's on the x's that we're talking about. That's where it really matters. Whoops, accidentally. There you go. Not polynomial since the power of x is 2/3. That's what makes it not polynomial. Okay, let's look at the next one. What do you think this time? Will this be polynomial or not polynomial? Very good. Why is that the case, Jesus? It has a root. You cannot have a root of x. Again, you can have a root of a number, but not of x. So not polynomial. Not polynomial. I'm going to copy this down and just change it. It's not polynomial since there is a root, since there are roots of x. You cannot have a root. You cannot have any type of root of x. That's the rule there. Okay, so for this reason, it's not polynomial. Both those roots. Okay, now let's go look at B. Or I'm sorry, C. Flip your packet. All right, on C, part C, what do you think? No, why not? It's dividing by x, not polynomial. By the way, I want you to know this. dividing by x is the same thing as a negative power. So put an equal sign here, and you can rewrite this. If you wanted to send this up to the numerator, a rule of mathematics is you could rewrite this as 4x to the negative 2 power minus 7x plus x squared. These are one and the same. These two things are one and the same. Dividing by an x squared is the same thing as multiplying by x to the negative 2 power. I'm saying it again. Dividing by x squared is the same thing as multiplying by x to the negative power. That's what a negative power is. And so you're correct in the assessment that it's not polynomial. Not polynomial since in the original, dividing by a power of, or since dividing by the x variable. And I'll say you cannot divide by x or have x as with a negative exponent. Okay, how about D? What do you think when you look at D? Polynomial or not polynomial? What's your thoughts as you examine that one? Not? Augustine, why not? What do you see? Yep. Yep. Negative exponent, all those reasons. Okay, now this one, we're going to do something different. You're going to like this one because you don't have to write as much. Not polynomial, dot, 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 until we simplify. Now, what do I mean? This can become polynomial. So I'm going to start with x cubed divided by x. Do you know what x cubed divided by x is? Very good. This becomes x squared. Okay, now, next one. I told you a second ago, what can you do with a negative power? I showed you right here. What can you can, if you want to get rid of it, you can move it from the denominator to the numerator and vice versa, and you either add a negative or you drop the negative, depending on which way it starts. So this is the same thing as 2 times, instead of 2 divided by x to the negative 2, it becomes 2 times x to the, this would become a negative negative 2 power. What happens with a negative negative 2 power? It becomes positive. This becomes a positive, and so we could just say that is 2x squared. Okay, how about this? What happens when you take a square root and square it? What's the relationship between a square root and a square? They cross each other out. And so this one, those cancel, and we're left with x. And finally, do you know what anything to the 0 power is? This pi to the 0 power is equal to 1. Someone said that. I don't know who said it, but great job. That is 100 Angel. Well done. So how could I rewrite this function? I could rewrite it like this. G of x is equal to, we said x cubed over x is x squared plus 2x squared plus 1x, and then finally plus 1. Now that you could actually simplify one. I probably should go back and change this to like a 4th power, because these two can combine together. If you wanted to simplify this further, you could say those combine together, and we could actually write g of x is equal to, what's an x squared plus 2x squared? Is that 2x to the 4th power, or is that 3x squared? You have 1x squared plus 2x squareds. That's 3x squared. You could actually rewrite this as 3x squared plus x plus 1. And that right there, is it polynomial or not polynomial? This is polynomial. All right. Let me get this where it'll stay together. That right there is polynomial. And so if we reduce it, it becomes polynomial. At the start, though, it wasn't, but at the finish, it is polynomial. So why did I do that? I just wanted to show you how some of the math works. So don't get too much of a hurry. Make sure you simplify first. Always simplify first and then identify if it's polynomial or not. In this stage, it was not polynomial because of those rules. In this stage, it is polynomial. All right, with that, I have some for you to try. I say some, I'm sorry, not some, but I have one problem. I want you to simplify this. I want to make sure you know your rules. Algebra, this is the one rule I did not do. I want you to apply whatever mathematical rule you have to, because like I said on this one, if you can simplify first, then testify whether it's polynomial or not. Polynomial functions should only be adding and subtracting. Right now I have multiplying. Distribute that to get rid of that, and then identify if it's polynomial or not. DOL number 1. Okay, now let's talk about the pictures. Here, this gives you your rules. All right, this just gives you the rules. You can read over this later. What am I going to say over here? To be polynomial, it'll be a smooth, continuous curve. What it will not have, is the picture will not have any breaks, jumps, gaps, chasms, vertical asymptotes, cusps, or sharp turns. Basically, what I'm trying to say is, if it's going to be polynomial, it'll all be connected. That's what continuous means, connected and smooth, meaning you could draw it without picking up your pencil or doing a jagged edge. Okay, so take a look at the first one. What do you think? Polynomial, not polynomial. Not polynomial. Let's say, or we'll write that in there, not polynomial. It's not polynomial because what did you see that makes it not polynomial? The break, and a hole would also make it not polynomial. That one's the hole's not as obvious as the break, but that is not polynomial. Very good. Okay, what about the next one? This is polynomial. Why is it polynomial? It's continuous and it's without breaks. It's without jagged edges. It's without sharp turns, anything like that. So this is everything's rounded and it's continuous. So that's polynomial. All right, how about C? What do you think about C? There you go. I'll give you a chance to flip your page. You are correct in your assessment. Now this is continuous, meaning you don't ever pick up your pencil if you drew it. But why is it not polynomial? Those jagged edges, those points, those corners. A polynomial equation could not create that. It would take a different type of equation to create that. What about part D? Polynomial. That's what a polynomial would look like. Smooth and continuous. That would be polynomial. All right, so now we're going to switch into calculator. How do we identify some polynomial key attributes using our technology? And specifically, there are a bunch of vocabulary words you're going to hear me say today. You can look through here. Remind me, what did I say is true about the domain on a polynomial? Remember, we're not dividing by x, we're not taking a root of x, and we're not taking a logarithm of x. We're not breaking those 3 rules. What will the domain be? All real numbers. That's what this is saying here. 0. I want to go ahead and put this note I did not include on here, but I want to include it here. The maximum number of zeros is equal to the degree. Now there is a vocabulary word again. What did degree mean?
The power of the leading term.
Yeah, the power of the leading term, or you could say the greatest power. Either answer is acceptable. The maximum number of zeros is equal to the degree. Okay, that's going to be a key thing that's very important to understand. The maximum number of zeros is equal to the degree. It doesn't have to have all the zeros, but it cannot have more than the degree. It's impossible to have more than the degree. So here are 3 examples to show you. Okay, so to show you what this means, this is the only vocabulary word that I think I'm going to draw attention to. Is I'm going to first give you a linear equation. Let's say the equation was y equals mx plus b, linear. What's my power of x if it's linear? 1. Okay. I'm gonna draw a line here and tell me, oh, what is a 0 again? Do you remember? An x-intercept. How many x-intercepts does this line have? 1. Okay, well, what if I moved it? What if the equation had the line like that? How many do I have? Still 1. What if it was like this? Still 1. Okay, well, what if it went this way? Still 1. No matter what, a line has how many zeros? 1. Now here's the deal. Odd powers will always have at least 1. It's not true for evens, but odds will always have at least 1. Since it's power 1, you'll always have 1. Okay, let's go to example 2 here. I'm going to go to an even power this time. Let's do a quadratic function. So a quadratic function in general form would be y equals ax. It's going to have a squared there, but I'm going to write it in red. It's ax squared. What's the highest power? 2. Okay, I'm going to draw my parabola, and I'll show you right now how many zeros does this parabola have? 0. So an even power does not have to have zeros. It could be like that. But what's the maximum? Well, how many does it have right there? 1. How many does it have there?
2.
Could I ever make it have 3? What if I moved it over here? What if I flipped it upside down? Could I ever make it have 3 zeros? No, the maximum number of zeros is 2. Does that make sense? We could keep going on and on and on. Do you want me to show you one more example? You want me to show you cubic? Or you got it? You want to see a cubic? Let's see a cubic. So a cubic example. The equation would look like very similar to this, but you just add an added term. So it'll be ax cubed. Let me put the 3 there. Ax cubed plus bx squared plus cx plus d. That's the general form. And a cubic can look like an S curve. So I'm going to draw an S coming up, down, up. Okay, on this S curve, how many zeros do you see? 1, 2, 3. What if I shifted it down? Now how many does it have?
3.
Okay, what if I shifted it to there? Now how many? 2. So notice it doesn't have to have all of them, but can I ever get to 4? That's 2. The smallest this could ever have is 1. Odd powers always have at least 1. Even powers don't have to have 1, but odd powers have to have at least 1. Questions over that? Okay, so how many zeros can a function possibly have? The maximum, which is equal to the degree. You got it. Okay, here's some more other words that'll come up. Today the new vocabulary word we're gonna find is maximums and minimums. My guess is you don't have to have me explain, but it says here the point where the polynomial switches from increasing to decreasing. It's gonna look like a hill. Because we don't have jagged edges, everything's rounded. It's going to look like a rounded hill if it's a maximum, a rounded hill, the top of a hill, or a minimum will be the lowest of a valley, like if you're going through a valley. And again, nothing's jagged, everything's smooth. So the bottom, the very bottom on that. Also, we could have maximums and minimums at endpoints, which I'm about to show you in a second. Okay, so there's all your vocabulary words. You can look back at these at your leisure. Here's a diagram to show you through. Hey, quick question for you. How many zeros do you see? 3. So from what I've taught you so far, what's the minimum power that the equation that I used or that the textbook used to create this graph? What's the minimum power this could possibly be?
0.
Nope. If it has 3 zeros, it has to have a minimum power of 3. Could the power be bigger than 3? Yes. Could it be smaller than 3? No. Could be 3 or bigger. We'll learn in coming days that it actually has to be an even number because both the ends go up. We'll learn that in lesson 1-7. So I know it has to be an even number because both the left and the right go up. Since they're going the same direction, it has to be even, but you don't know that yet. So right now you just say it has to have at least 3 powers to create that. Okay, so all that is for you to look back on later. After him. Okay, so let's take a look at example 3. Here's what we're going to do in the calculator. Very important thing you need to learn how to do. This thing right here is called a restriction. Circle this up right here, this -8 to 4. This is called a restriction. we will frequently be dealing with restricted graphs, which means we're not going to look at the whole graph. We're going to cut off the graph at the x value of -8 and the x value of 4. So here's how we do that. Open up your calculators. I want you to go to New Document. Hit New Document. Don't save if it asks you. Don't save, and then go to Add a Graph. We're going to type in the equation x squared plus 4x minus 12. Don't press enter. Just get that part typed in. Are y'all there? Got it typed in? Okay. Now this restriction, if I press enter right now, this will be a parabola that goes forever both ways. And that's not what I want. I want it to only go from -8 on the x-axis to +4 on the x-axis. I want to cut off the graph. I want to restrict it. Okay, here's what I want you to do. Press the Control equals button. When you press Control equals, they have these inequalities in there, and they have one that doesn't seem to belong. It's called a pipe, this straight line. This in the calculator tells it you're about to do a restriction. So press the pipe, the straight up and down line that's in the Control equals. Press pipe. That's going to tell the calculator we want to cut off the graph. We want to cut it off starting at -8. And our calculator is built where you could cut off x's or y's. So you have to tell it which letter. You can't just do a comma. So go back to Control equals. And the only way I know how to do it is to say that that's the smaller number. So less than or equal to x. And then we're going to say less than or equal to, and now we'll do the positive number 4. And this will cut off any values that have a smaller x than -8 or a larger x than +4. So if you wanted to cut off y's, which we won't ever do in my class, you could change that to a y, and you could do that. You could cut off the graph. Okay, press enter. And right now, you might not be able to realize it's cut off, but it actually is. Hear me. In my class, whenever we do a restriction, we're always going to follow it up by doing a zoom fit. We won't do zoom fit if there's no restriction. I want you to hear me closely. Zoom fit is great if you have a restriction. It's terrible if you don't. So I want you to press the menu button, choose Windows Zoom. You will see the letter A says zoom fit, but before I click it, I want you to look at my picture. You see how it has a curve? What are those two blue symbols that are pointing at the curve? What are they doing? Which way are they pointing? This one up and this one down. What zoom fit will do is it will not change the x values. It'll only change your y's for the given x values on your screen. Because we told the calculator we want it from -8 to 4, it'll fit in -8 to 4. So you see how it gave us, how it shows us the top of the graph and the bottom of the graph? That's what we want. Now, let me say this again. If there's not a restriction though, our graphs are going to go on forever and it'll zoom way off. We won't be able to see it because they're going to zoom so far off. So for that reason, we only do zoom fit if it has a restriction. Okay, here's what we're doing today. We need to be able to discover domain. We need to be able to discover minimums, maximums, stuff like that. So I'm going to show the calculator how to do that. Press the menu button. So what we're going to choose is analyze graph. Whenever we're doing calculator, finding key features, we're going to go menu, analyze graph. Here's where we can get our key features. The first one up is 0. So I'm going to click 0. A 0 is an x-intercept. So as I look at this graph, I see there are 2 x-intercepts. There are 2 zeros. What I'm going to do is with this dotted line, I'm going to go to the left of that 0. That's because this word down here says lower bound. That means the number that's smaller. So you pick an x that's smaller than that 0. So I'll just go to the left of it, and I'm going to click with that center button right there. The center button. So once you're on the left, click with your center button, and then it'll change the word to upper bound. And that means you go to the right of the 0. Once you do that, it'll show you the point of -6, 0. You got the same value as me? Okay, I want to do it again. Now this one, I know we can see it's at 2, but there are going to be problems today later where we cannot tell where it is. So I'm just going to show you how to do it. Again, menu, analyze graph, choose 0. Even though I can see it's at +2, I'm going to just show you. I'm going to go to the left. I'm going to click with the center button, and then I'm going to go to the right. And I'm going to click with the center button. And the calculator does, in fact, tell me it's at 2. Y'all getting the zeros? Okay, now let's go back to analyze graph, and this time, the next one that comes up is the minimum. Let's find out what this minimum value is. So calculator, analyze graph, I want you to choose minimum. So again, it's gonna say lower bound and then followed by upper bound. So I think the minimum is somewhere in here, in this range. So I'm gonna go to the left of it, and I'm gonna click. And then for the upper bound, I go to the right of the minimum, and I click. And it should give you the points. What point are you getting for your minimum? -2, -16. Good. Okay, now this graph has what we call endpoints. Because we restricted the graph, it has ending. If you have endpoints, those are automatically either minimums or maximums. On this graph, those are both maximums because they're taller points. So these are going to be maximums. Let's find those. Go menu, analyze graph, choose maximum. I'll find this first one on the left. Again, it says lower bound down there. So I'm going to go to the left of the maximum and I'm going to click. So I'm to the left of the maximum. And then now for the upper bound, I'm going to go to the right and I'm going to click again. And I'm getting -820. Last time for this problem, I'm going to go menu, analyze graph, and we're going to find the other maximum. So I come over here, I go to the left of it for lower bound, click, go to the right of it for upper bound, click again. And I get +4, +20. Hopefully you just got the same values as me. Now we can put in our values. So here's how we're going to write our values. For zeros, when they say zeros, it's assumed that you know the y value is 0. So all you have to put is what the x values are. What x values are my zeros located at? Try that again. I heard 6 and 2. Be more specific. -6 and +2. You can just separate them like a comma like that. Now for maximums and minimums, we can't assume a x or a y value, so we have to put them both in. And the way we're going to do it in my class is following the model of y is equal to f of x. What do I mean by that? So a maximum, a relative maximum means any maximum whatsoever you see in the graph. This is a maximum right here. That is a maximum. What I'm going to do is I'm going to say f of the x value, which is -8, equals the number 20. So what I did here is I plugged in the place of x, the -8, and I put the y actually at the end here. I put 20. We've tracking with me so far? Now I have a second maximum. So you could do a comma and write this one in. F of, what's my x value? 4, and that's equal to 20. Now I wrote it out the long way. You see how the y values are the same values? If they share the same values, there is a shortcut. Here's how the shortcut looks. You don't have to erase yours. That is the correct answer. But if you wanted to, you could shorten it and write it this way. You could say that f of -8 is equal to f of 4, which is equal to 20. What am I saying? The function at -8, is the same thing as the function at 4. And what do they equal in both situations? 20. So that's a shorter way of writing it. If they're the same number, you can do it like that. Okay, tell me about the minimums. How many minimums do you see? 1. How would you write that? You see if you can tell me. F of -16? Like that? Would that be right or wrong? F of -2. You put the x value in there. F of -2 equals -16. That's how you would write that. Okay, so now what's this word absolute mean? So relative means that it's a maximum on the graph. It's a high point on the graph somewhere. Absolute means that the graph never goes higher or never goes lower. Are these 2 points the absolute highest points on the graph? We have to put that. Yeah, they are. So we're gonna copy the exact same thing down here. So this problem The maximums, both maximums listed were the absolutes. That's not always the case. Okay, tell me about this minimum. Is it absolutely the lowest part of the whole graph? Okay, so it's same answer as relative. Here in a second, I'll show you how they could be different answers, how you could have a minimum, but it not be the lowest point in the entire graph. Okay, make a note. These four, we're going to write our answer using intervals. There's a vocabulary from previous days past. What does it mean to be an interval? X values. And when you do intervals, you don't have to ever use brackets. You can do only parentheses if you like. So intervals, it's totally acceptable to only do parentheses. And so that way don't risk messing up with a bracket. I'm just going to use parentheses all the way down. Does our graph ever decrease from left to right? Does it ever go down? Yes. From where to where? What? Just talk X values. Only X values. I should put that in parentheses. Intervals means X values. From -8 until -2. Very good. Just put it in parentheses, -8, comma, -2. You got it right. Do we ever increase? -2 to +4. Very good. Again, intervals, you only look at X values. Now this graph, is it concave up or is it concave down? Concave up. And it's concave up the whole time. So from -8 to 4, we're going to put concave up. From -8 to +4. I think I might have just said -4. From -8 to +4, it's concave up. Is the graph concave down? If it's not, I just do N/A for not applicable. That's what I do. I don't leave it blank. I always put something there, so I just do NA. That's what you see me do. Okay, now lastly, inflection points. An inflection point occurs when you switch from concave up to concave down, or switch from concave down to concave up. Easier way of saying it, you have an inflection point if you change concavities. Do we ever change concavities? Nope, so this is none here. Since these are points, I'm going to go back to red. Red will be for my point. If I'm listing a point, I'm going to do it red. If it's an interval, I'll do it in green. So no inflection points. So that's how I do it. That would be example A. All right, you saw me do it. Let's reload and try it again before I let you try one yourself. Let's go to part B now. So I'm going to start all the way over. I'm going to hit home screen, new document. The reason I'm doing this is it'll reset the window. Remember how we did Windows Zoom last time and it changed it? This will reset it. If you go home screen, new document, it'll reset and it'll take off all those other points that we already found. My equation this time is x cubed plus 1. X cubed plus 1. And while you're typing, what does it mean, this little bracket, -2 to 2? What is that telling you? That's the restriction. That's going to cut off part of the graph. So we got to add that restriction to the calculator. Do you remember how to add the restriction? Do you remember what we pressed? Control equals sign. There is one inequality. These are called inequalities because they're not equal signs. They're everything but an equal sign. There's one thing in the inequalities that does not seem to belong with the others. Which one does not belong? The line. That's called a pipe. Click the pipe. So -2. That's the smaller number, which means less than or equal to. This is a smaller number. -2 is less than or equal to. What's our variable we're going to tell the calculator? X. We're cutting it off based off X values, which is less than or equal to +2. In my class, it'll always be these three symbols on a restriction. Always. We will always do less than or equal to X, less than or equal to in the middle. It'll always be that way. So one of the things I tell my students is I had a student years ago said the Pac-Man symbol. That's fine. Think of Pac-Man always trying to exit class. Pac-Man's trying to go out the door. So which way the inequality symbols always go? That way. That'll always be true all year. So if you're taking your AP exam, you're going to put it in that way every time. All right, press enter. The graph looks like it's going off the screen. But because of the restriction, it should not go off the screen. What buttons do we press to see the whole graph? Zoom fit. And like I said, we will only do zoom fit if we have a restriction. We will never do it if there's no restriction. Do zoom fit. Yeah, once Jesus gets back. All right, let's start filling in some points on this one. Just tell me, what do you see that this graph has? Start with zeros. How many zeros do you see? Though it has an ability to have 3 zeros, it doesn't have 3 zeros. How many does it actually have? Only has 1, even though it has the capability of having 3. Let's go menu, analyze graph, 0. So click on the left of it, click on the right of it. Okay. What else do you see? The next one on our list is minimum. Does this graph have a minimum? Yes. If your graph has a restriction, you will always have a maximum and a minimum. You will always have a maximum and a minimum if your graph is restricted. So this has a minimum at -2, -7. Do you see a maximum? Now here's a question for you. Do we see one maximum or two? So let me find the one that we know is a maximum, and then we'll talk about the other. Okay, remember how I told you a maximum is the top of a hill and a minimum is the bottom of a valley? I did not say a maximum is the top of a cliff or a minimum is the bottom of a cliff. I said hill and valley. So here's my question for you. A hill means it goes up and then it comes down. A valley means it goes down and then it goes up. Does this graph actually make a hill around the y-axis? Does it go up and start to go down?
Yeah.
Do you see it go up and down? Or does it just go up and flat? That is not a hill. So that is not a maximum and it's not a minimum. We're going to call that a point of inflection here in a second. But it's not a maximum, it's not a minimum. See how it doesn't make a full hill? Nor does it make a full valley. Because it doesn't go up and down, it's not a maximum. Make sense? The calculator does not show us what the I forgot to tell you this in the last one. The y-intercept, where does it cross the y-axis? The calculator doesn't have an analyze for that, but it's always the number that's all by itself. What does this number say right here? That means it's hitting at 1. All right, let's copy that over. And we will fill in our features. So here's our equation. So zeros, how many zeros did we find? 1. Even though the cube means there was a potential for 3, only 1 existed because the graph was shifted up. That's why it only had 1. The 0, you just say x equals -1. Now this time you're going to see me use the letter g because this equation, so this time it's going to be following the pattern y equals g of x because they use g on the equation. So maximum, how many maximums do you see in this graph? 1. There it is. So we'll say g of 2 equals 9. What minimum do you see on this graph? Just this one. G of -2 equals -7. Now, is this an absolute maximum? Meaning, does the graph ever go higher?
No.
Never goes. So it is or is not an absolute?
It is.
It is an absolute. So you copy your answer that we just had earlier. The next example will have where they're different. You'll get to see that. Is this an absolute minimum of the graph? Yes, that's the lowest it ever travels. So that is an absolute minimum. Okay, going left to right. Let me make my note. These are intervals again. What does intervals mean one more time? Yeah, we're only going to list the x values. We're not going to list the y values here, just the x values. Does my graph decrease as I go left to right? Nope. So I'm going to do NA. Let me add that point here, the y-intercept. I'm going to add that for our notes, which is at 0, 1. That's going to help us in a moment. Increasing. Does the graph ever increase as you go left to right? Technically, it's always increasing. Even in here, it's still slightly increasing. So we increase from start to finish. Where do I start? -2. Good. I was wondering if you'd say -7. Remember, we only go off x's. So from -2 until +2. Okay, concave up or concave down. All right. This graph. Remember, concave up. If you're curving, you're either concave up or concave down. This graph is always curving. So it's always one or the other. Does this graph look like this part that if rain were to hit, that it would catch the rain or the rain would spill off of it? Spill. That's concave down. If it spills, it's concave down. Over here, what would happen on this side? Would it start to catch it or spill it? Start to catch. So this is concave down. This is concave up. So we're concave down. And again, x values. Concave down from -2 until not 1, that's the y value, till 0. -2 until 0 is concave down. Concave up from, oh, I did the y this time, from 0 until 2. Good. Here's my question for you. Will we have an inflection point?
Yeah.
We do. Why do we have an inflection point? Because we switched concavities. What's the point where we switched at? Is it -2, 0, 0, or +2? Where did we switch at? 0. So the inflection point is g of 0, which equals, what is the y value at 0? 1. There it is. Cool? All right. I'm going to sneak in one more before I ask you to do one. I'm going to sneak in one more, and then I'm going to ask you to do one, and we're going to use Desmos next time. Actually, let's do Desmos now so that you know how to do both. Let's do that. Take out your cell phone and go to desmos.com. Yeah, go ahead. He's got it. That's what I was saying. So go to desmos.com. This is what I recommend for you to use when you're at home without me graphing. And I'm going to type in the equation exactly as it's given. H of x equals x cubed. I even type in the h of x. Minus 3x squared minus 4x. Okay. Now that we have this equation typed in on Desmos, here's how you do a restriction. Now, click your keyboard's probably automatically up. Mine wasn't on the computer. If you have like an iPad or something like that, your keyboard might not actually be up. So open up the Desmos keyboard. Here's how you do a restriction. On theirs, you press the ABC button and you use this squirrely looking bracket. That bracket right there, that's what we're going to use for a restriction. And then we'll type it in just like you would on my Inspire calculator. We're going to type in -2 is less than or equal to x, which is less than or equal to 5. Okay, so that's how you'll type in the equation. The biggest issue with delta math is it doesn't have a zoom fit. So here's what I'm going to do real quick. I'm going to look how high the graph goes. When I come up here like this, oh my goodness, how high does this go? Okay, when I click the graph, it tells me how high does it go? Nope. See how it says 46 there? And then I'm going to scale down to see how low does it go. So it goes up as high as 46, and how low does it go? -24. So here's what I do now. Hit the wrench. What I'm going to look at is on the x values, I always just leave my x as -10. If you hit the wrench, you can change the settings. Where it says x-axis, I want my x-axis to go from -10 to +10. I leave the x-axis that. But I just found out I need to get as low as -24. I pick a smaller number, and I usually go to the next 10th. So I'm going to type in -30. And then the y value for the top, it went as high as 46. So again, I usually go to the next 10th, which would be 50. When you click that, it'll show your graph really well in there. You can see the top and the bottom. It's kind of like zoom fit. Okay, I've been informed that my equation's not right. Let me put an X in there. Okay, so my equation, it's bigger than it needs to be. Okay, so it looks like I didn't need to go as high as I did I? But I have extra. It's okay though, as it is. Now here's what I like about Desmos. Check this out. On your screen, this is called a maximum there. Just click the screen right there. And you see how it shows you the point? You don't have to do a menu analyze, anything like that. You just click and touch. Go ahead and click that point, this point, this point. You can click all the points except for the endpoints. You can click all of them like that. So I'm going to take this and I'm going to copy this over to my notes. And I'm going to fix this later. I'll come back and add it to where you can see the equation. Actually, I'll do it right now. I'll give you a second just to. Okay, so there's my equation I typed in. Okay, and now we'll get our values. So there's only two values that are not on the calculator. We need to find out the maximum and the minimum. Click on your graph and move your finger to the top. What are you getting for the top? Are you getting 5,30? Okay, so I'm going to add that on my picture since I couldn't click it. Originally, I couldn't screenshot it, I should say. That is 5,30. And then let's go find out what this point is right down there. I'm going to, again, click your graph. You can move your finger through it. That's what's nice about Desmos is analyzing. What are you getting there? There's -2, -12. Great. -2, comma, -12. I'll put that on there. -2, comma, -12. All right. So zeros. How many zeros did this graph have? 3. All 3 that were possible. So x equals, the first 0 looks like -1. These are my zeros, the ones that have y's of 0. So it'll be -1, 0, and 4. I always go in order from left to right. You're not incorrect if you don't, but it's just a lot easier if you go left to right. And this one is a h of x. So all my points I'm going to put it in the form y equals h of x. That's how I'm going to write them out. Relative maximum. Do you have any maximums on this graph? That means endpoints that are maxes or top of hills. Do you see any? How many maximums? This has 2. Let's go only 3 decimal places here. We're going to say f of, this is a maximum, -0.527 or 528? 528. Now, are the two y values the same this time? No, I got to write them separate. So I'm going to write this one equals 1.2, or sorry, 1.12. Then do I put an 8 or a 9?
8.
8, good. There's the first maximum. The second maximum will be easier. F of 5 equals 30. How about minimums? How many minimums do you see? So this was a max. This was a max. This is a min. This is also a min. So we have 2 minimums. So left to right, the one on the far left is -12, f of -2. Oh, I'm putting f's. What letter should I be using?
H.
H. Goodness. I'm sorry. I'm sorry. Okay, h of -2 equals -12. And h of, here we go, rounding again, 2.52. Will we say 7 or 8? 8. 2.528 equals -13.128 or 129? 128. Now, absolutes mean it's a maximum and it's the highest point of the whole graph. How many absolutes does this graph have? Only one. F of 5, thank you. H of 5 equals 30. And how many absolute minimums do I have? 1. H of the x is positive. 2.528. The x value is positive, but the y is what's negative. Equals negative 13.128, we said. Now, what can you tell me is going to be true about these next 4? How do we write those in? Intervals. Okay. Where are we decreasing from? Do we decrease?
Yes.
Yes. From this maximum to this minimum. So from negative 0.528, we said. That's this x value until this minimum value, which is 2.528. We decrease there. We increase twice. So here's how you write that. You increase from -2 up until this value here, the negative 0.528. And what you do, since I increase the second time, is you do a union. It looks like a U. And then you do another bracket. So from here, it would be 2.58. 528, sorry, 2.528. All the way up until 5. We increase again. How about concave down and concave up? Are we ever, what's this first part of the graph? Concave down, and now we could click and find the point. I know the math here. You the concavity changes, right? Oh, this is not even showing me. It's that, there it is. 1, -6, that's where it actually switches. You don't know why yet. I'll show you why later. It's there. But I'm going to add that point to my graph. 1, -6. 1, -6. I'm going to add that to the graph right here. This is where we're going to have our reflection point. So I'll go ahead and put that as a reflection point. H of 1 equals -6. That's where we're going to switch concavity. So we start concave down from -2 up until, what did I do over here? I just realized I moved my picture somehow. There we go. Let me get this back on the right spot. There you go. We're concave down from -2 until the x value of 1, and we're concave up from this value of 1 until 5. Questions on how to use Desmos? All right, D. All right, we're going to take one more look on 3D here. So I'm going to come back over to my Desmos. What you can do is, if you're on the web page, just hit the refresh, or you can just hit the X buttons. But either way, I want to zoom it back to normal, or you could have hit Z, the wrench. No, I don't remember how to reset other than to hit refresh, or you can just close the app and reopen it. I'm starting fresh. Okay, I want to type in the equation. F of x equals 4x squared minus x to the 4th. Hey, quick question. What's my degree on this function? Very good. It's the highest power, so the degree is 4. Does this have all 4 zeros? It only has 3. Okay, now let's restrict. How do we restrict on Desmos? You go to the ABC side and you do a squiggly bracket. Whoops. I need to leave the power. Squiggly bracket. From -3 less than or equal to x, which is less than or equal to 3. Okay, I'm going to kind of slide down till I see where the bottom of this graph is. Okay, it looks like it goes as low as -45. That's what my calculator is saying when I'm clicking it. So I'm gonna hit the graph settings. I'm gonna make it where it's easier to see. I know the x's, I only need to be able to see from -3 to +3. So I'm gonna do -5 to 5, just so I can see a little bit past it. That'll be our x-axis. And our y-axis, I need to see, what was it, -45? Okay, I wanna make sure I can see a little bit lower, so I'll do a -50. And it doesn't go that high. I don't know, 25 maybe? I'll just do 25. And so that zooms my graph different. Okay, I wanna click on the button, it's the key values, the critical points is what they're called. I think I got all of them. It won't let me click those two, so I'll take a picture of that. And I'm gonna come back and fix the equation here in a second. Okay, now that I have it reset, I'm gonna go add the two minimums. It was -3, -45, and +3, -45. I'm gonna add those in. -3, comma, -45. This point here, -3, -45. And this point here, 3, comma, 45. So first question for you. How many zeros did you say we have on this one? 3. What are the values for our zeros? -2, 0, and 2. Whoops, don't need a parentheses. This is called f of x. So I want to write my other values in the term in the function notation y equals f of x. Relative maximums. Do we have any maximums? Yeah. Okay, this time, just to make it quicker, let's go 1 decimal. So -1.4, -1.5. Okay, now before you put equals 4, check out, what does this maximum equal? A shortcut, if they both equal the same value, is you can say f of -1.4 is the same thing as f of 1.4, which equals 4. You can say f of -1.4 equals f of 1.4, which equals the value 4. Just a quicker way of writing that since they're one and the same value. Do we have any relative minimums? How many minimums? 3. So I have these two. I'm going to use shortcut way again. F of -3 equals, since these are both in, I didn't put -45 there. No one corrected me. -45. There you go. I'm going to say f of -3 equals f of +3. And what do they both equal? -45. Now I'll do a comma. This is a valley as well. The bottom of a valley. I'm decreasing, now increasing. That's a minimum. F of 0 equals 0. There it is. F of 0 equals 0. Okay. Absolute maximum. Do we have any absolute maximum? Highest points of the graph? These both are. Those are both absolute maximums. So -1.4, f of -1.4 is equal to f of +1.4, which is equal to the maximum value of 4. Very good. Do we have any absolute minimums? Both of these 2 points are the lowest points of the graph. So f of -3, which equals f of 3, which equals -45. You got it. Okay, these will be our intervals. Decreasing. Does this graph ever decrease? Yes, from where to where? I hear -1.4 to 0. I agree with that. That's decreasing. And again, intervals means x values. So that's why we're only doing x's here. X values. Okay, so -1.4 to 0. Anywhere else it decreases? 1.4 to 3. Good. From from 1.4 until 3. How about increasing? Do we ever increase on this graph? -3 until -1.4, good. And we also increase from 0 to 1.4. Now, because we're increasing and decreasing so many times, there's a lot of concavities going on. What is going on first? Concave down, and it's concave down up until some point in here. Now I'm gonna estimate. I don't even know where to estimate. I don't even know where to estimate right now without doing the math. I could, well, so I don't estimate, I'm gonna figure it out. I'm gonna do my calculus real quick. Minus 4x cubed. It's -1.8165. That's where it's gonna be at. And then also positive, that's okay. 8165. So right in 8165 is approximately there. That's about the inflection point. So can y'all remember that? -0.8. Let's just say -0.8 and 2.2. -0.8 and 2.2. I'm gonna add that in. Right in here. -0.8 and 2.2. Wow, that's way too small. Let me try this again. -0.8 and 2.2. That's that point, and this one would be almost the same point, but positive 0.8. Okay, now you don't know how to get those, but that was by doing a calculus trick. Okay, so concave up, or what do we say we're doing first? Concave down. So we are concave down from -3 until -0.8. Union, we have another place for concave down. Positive 0.8 to 3. Very good. And we're concave up in between. -0.8, whoops. From -0.8 until positive 0.8. We're concave up. So we have 2 inflection points. The 2 inflection points would be f of, there's a shortcut way of writing this. -0.8. The shortcut is, since they're the same y value, f of -0.8, which equals f of positive 0.8, which equals, what's the y value? 2.2. There we go. Okay, from here, you have the DOLs on the packet, where you can look at this one and this one, and then you can jump on to AP Classroom for lesson 1.4.